response of RC coupled amplifier. The frequency response of RC coupled amplifier. This frequency, and this is transfer function or gain model transfer function. Okay, and here specifically, if I say you to draw the frequency response of RC coupled amplifier, it will be like that. Right? And there are certain limits, like this at this scale, this is having maximum value 1, and at this scale, this is having some less value. And in decibels, if you will see, this is 0 dB, and in decibels, if you will see, this is minus 3 dB. It's minus 3 dB equals to 0.6707. Okay, and here this is called lower cutoff frequency. This is called upper cutoff frequency, higher cutoff. Okay, and this is called bandwidth. Fine. So these are also known as 3 dB cutoff frequencies. 3 dB cutoff frequencies. Okay, fine. And you know, have you studied that maximum power transfer theorem?
Yes, sir. Yes, sir.
Yes, yes. Bandwidth means the operating frequency band of an amplifier, and this is equals to fH minus fL. Okay, and what will be the unit of bandwidth? What will be the unit?
Frequencies of hertz.
Hertz. Okay. Yes, yes. So this is the frequency response of RC coupled amplifier. Okay, just please keep this in your brain. Now this is second unit finished today, and I'm going to start the next unit. Field effect transistor. This can be categorized into two parts. Junction field effect transistor is known as JFET, and second one metal oxide conductor resistor. This is called MOSFET. Okay, and this MOSFET can further be categorized into two parts. depletion type MOSFET, and enhancement type MOSFET. Fine. So we'll finish this syllabus and we'll perform the operation and characteristics of these all three devices, and after that we'll move towards the biasing and related small parameters. So I hope that within this week we will try to finish this unit. Okay, so one question is this: difference between BJT and FET. What is the difference between VGT and FET? So here on the left side I am writing VGT. On right side I am writing this FET. So first difference symbol. Okay, collector, base, emitter. This is NPN, and this is collector, base, emitter. This is PNP. And symbol for FET is something different. For N channel, and this is for P channel. Here's the concept of channel. Okay, either the concept of base region. There are three terminals: collector, base, emitter. Here are three terminals: drain, gate, and source. Drain is equivalent to collector that collects the electron or charge carriers. Gate is equivalent to base region, base, okay, and source is equivalent to emitter. Second one, this is current control device. This is voltage control device. Many times this question was asked in different PSUs: which one is the current control device, VJT or MOSFET? Which one is the voltage control device? This is less stable to temperature variations, provides high stability over temperature variations. Okay, and next one, offers less input impedance. Last time I told you, na, for making an amplifier, the input impedance should be very high and output impedance should be very small. High input impedance. Okay, these are four differences, and furthermore, this is fine. These are main differences. You must keep these differences in your brain always. Okay, fine. I don't think there is any doubt. Operation and Characteristics of JFET, junction field fat transistor. Operation and characteristics of JFET. Let me show you the symbolic structural diagram. This is a drain, this is source, and this is gate, this is gate. Okay, and here this gate terminal is short circuited at both. This is like biad connection. Gates are short circuited. Okay, fine. And this is drain. And here, this is very important portion. You see at how the gates are performed. Gates are implemented. Okay, developed in JFET. You see, we take N-type semiconductor, okay, and we make two P-type diffusions at different sides of this flap. P-type semiconductor, and this is P-type diffusions, and these diffusions we start behaving as gate. I hope you understood from the concept of that diode how the p-n junction diode is formed. In the similar manner, we take n-type semiconductor, we make two p-types diffusions at the different sides, and these diffusions we start behaving as a gate, and this is n-type channel, and this is the channel. Specifically, this is called channel. Fine, the remaining region. So you see, if I perform the operation of this JFET, first of all, here for performing the operation, suppose I am applying, what is the purpose? First of all, before applying any operation to this JFET, you just try to think about this structure. We need to source. What is the purpose of making this source? Source behaves as emitter and it provides the charge carrier. If this is n-type semiconductor, then definitely source will provide electrons. Okay, and what is the purpose of this using this drain? This is like collector drainage system. This collects the electron, means we are having electrons at the source end, and these electrons must reach towards the drain end, and drain will collect these electrons finally. And what will happen if this is the direction of flow of electron? Then definitely current will be flowing in this direction, and this current is known as IDS. Fine, drain current, ID. I hope you understood. So how can we serve this purpose? How we can fulfill this purpose? You see here, if this is drain end, okay, and this is n-type semiconductor, already we know, and we need to attract the electrons. So which polarity of voltage is required here at the drain terminal? Positive or negative? Tell me.
Positive.
Yes, this is good. Positive. Brilliant. Yes, yes, brilliant, brilliant. So we need to apply positive voltage at the drain terminal, and this voltage is known as VDS. So what will happen whenever we apply positive voltage? Electrons will start get attracted towards this drain from the source end. But simultaneously, what will happen due to this applied positive voltage at the drain terminal? Since this is n-type semiconductor and we are applying positive voltage here, so this junction. Ultimately, this is a junction region because this is a p-type diffusion, this is p-type diffusion, and this is n-type channel. So this is a junction we have created here. This is also a junction we have created here. So what will happen if this is reverse bias voltage applied here, positive or negative? Then at the junction region, one depletion region is created. Okay, you see, this is very interesting. The shape of this depletion region. Okay, what is the shape? Why I made this depletion region shape like that? This is bigger at the drain side, bigger at the drain side, and smaller at the source side. Okay, this is depletion region. Fine. Why this is bigger at the drain side? You can see here. This is bigger at the drain side because this is reverse bias here, and electrons are moving in this way. So this reverse bias potential increases, and that potential affects the depletion region at the drain side, and that's why the width of this depletion region is thicker in the drain side. I hope you understood what I just wanted to deliver to you. Okay. Simultaneously, one more thing at the first point. At the very first point, I'm taking the situation VGS equals to BP. I can also apply one voltage here between these two terminals. Okay, suppose I'm applying some voltage. Forget the polarity right now. I'm just applying. This is minus and this is plus. And do not decide the polarity. I'm just applying a voltage with, and this is I'm calling as VGS. And this is initially 0 volt. The first step I'm taking VGS equals to 0 volt. Okay, means this is behaving as short circuited, directly grounded. Okay, understood? Only I'm taking the voltage VDS, and this VDS I'm increasing. Okay, VDS is increased. So what is happening with the increased amount of this VDS? Electrons are being attracted towards drain from source, but simultaneously the depletion region width is increasing. This is the depletion region width. This depletion region width is increasing. And what will happen at certain amount of VDS, at certain amount of VDS, the width of depletion region is increased in the manner that whole channel is blocked. Understood? So what will happen if we are increasing this VDS, and at particular limit what happens, this channel will be perfectly closed. This depletion region will close whole the channel. Okay, and in that case, if this is fully covered by depletion region, this channel is fully covered by depletion region, in that case no electron will be passing from source to drain. In this case, no electrons will be passing from source to drain. Understood? And ID becomes 0. This is very. And one more important point, what is the value of that voltage? the value of voltage VDS for which channel is completely closed is called pinch of pinch off voltage, and this will be represented by denoted by BP. Okay, understood? So here in bracket at VDS equals to BP, ID becomes 0. I hope you understood. So at VDS and at VDS equals to BP, whenever VGS equals to 0, at VDS equals to BP, channel is completely closed because whole channel is fully covered by this depletion region and no charge carrier moves from source to drain, and there will be no flow of current because movement of charge carrier is not accepted. Okay, fine. And finally, you can see one more thing you can see. As this applied voltage VDS is deciding the width of this depletion region, so the amount of current is also being decided by this VDS. And one more factor is there existing there, that this channel region or this depletion region formed in this channel offers resistance to current. Okay, if current is flowing in this direction, then this, or if charge carrier is moving from source to drain, then in the path of movement of this charge carrier, this depletion region offers a resistance. Okay, and this resistance is very high or infinite whenever VDS equals to BP, and this channel behaves as open circuit for charge carrier and no current flows through this channel. I hope you understood whatever I just want to deliver in terms of electrical circuit theory. Okay, now tell me, is there any doubt?
N, whatever you write N, that is N channel, is there also N type semiconductor?
This is N-type semiconductor, and this region is behaving as channel for charge carrier, and we made two diffusions of P-type in different sides of this N channel or N-type semiconductor slab. Okay,
जिधर N लिखे उधर भी N type semiconductor है, ये doubt.
this is fully N. This try to understand this. This is N channel slab. This is N slab, full N-type semiconductor. We made two diffusions. Here we made two P-type diffusions in this N-type material. This is heavy dope. We made two diffusions, or we made doping like that. It behaves. This portion starts behaving as P-type semiconductor. This portion, understood? So this portion remains of N-type, and two P-type diffusions are there only. Understood my point? And this region, the N-type region, behaves as channel. Understood?
Done in a piece of metal, or the different types of semiconductors are joined here?
Similar process, whatever I have already explained during that discussion related to diode, that we use the diffusion process for making the junction, and there is no process like joining of two different types of semiconductor. Understood? We make the diffusions in a pure semiconductor. Fine.
Yes.
Understood? Any other?
रिवर्स बीएस में कैसे कनेक्शन है थोड़ा एक बार एक्सप्लेन कीजिए ना. N साइड तो P से पॉजिटिव से कनेक्ट है, बट P साइड नेगेटिव से कैसे कनेक्ट है?
I told you this P type. These are gate. Start calling them gate region. Okay. P type is gate. P type is gate. P is. I'll explain. This is the first step I have explained right now. And currently I took that, forget that I told you that forget the polarity of applied voltage. I just keep this VGS equals to 0 volt. So no matter how much the polarity is there. Second step I am moving towards. First step is clear to you? It's
Yes,
the
sir.
first. Yes, yes. I don't think there is any doubt. Okay, let me explain the second step. VDS, VGS is negative. Okay, and VDS increases. Fine. So what will happen? And so you see, this is the second step. VGS, we are applying a negative voltage here on the gate and source terminal. Okay, gate to source terminal, we are applying a negative voltage. VGS, this is being called as VGS. Fine, in second step, VGS, and this is negative. So you see what is happening exactly. Applied negative voltage here. This is P-type diffusions, P-type gate. So what happens at the P-type gate if we apply negative terminal, then it will create the reverse bias condition at the gate terminal. This is negative. So this gate junction is reverse biased. So what will happen? You see, always if we are applying reverse bias voltage, then it will affect the depletion region at the big level, and it will increase the width of depletion region. Already in the first step, you were having some conclusion that increasing the amount of VDS, by increasing the amount of VDS, we can increase the width of depletion region. Simultaneously, if we apply reverse bias voltage on gate to source terminal, then what will happen? The rate of increment in the width of depletion region will be increased. Means earlier VDS was reaching to the level of BP at which the channel was completely closed. When we apply negative VGS, this BP shifts to the lower position. Means for a small value of VDS, this channel will be completely closed. So this is another way to close this channel, to control this current, whatever is flowing between source to drain. So VGS is the voltage which can easily control the current which is flowing between the source and drain terminal. Understood my point? Do you understand this? So if you now third case, if you consider this VGS is the positive, okay, if you apply the positive voltage here, then what will happen? We need more value of VDS to completely close this channel. So you can see here, you can control the limit, you can control this BP, and you can control this ID by increasing the gate to source voltage or decreasing the gate to source voltage. Understood my point? So why this is called voltage control device? Because the current flowing between source and drain terminal is being controlled by the voltage applied between gate and source and drain and source. So that's why this is called voltage control device. Okay, I hope I am clear enough in my point. Here, the applied negative VGS increases the width of depletion region and depletion region, and VDS reaches to BP at smaller values. Try to understand this meaning of this line. The applied negative VGS increases the width of depletion region, and VDS reaches to BP. VDS reaches to BP, pinch off, at smaller values. I hope you understood whatever I just want to deliver. Second point, the applied positive BGS will cause will cause the larger VDS to be applied for reaching at level of BP. I hope you understood. The resistance offered by the depletion region
हेलो
to
यस सर बोलिए
charge carriers will be controlled by BGS and VDS, and hence current IDS as well. Okay, current IDS as well. So FET is called voltage controlled device. I don't think there is any doubt now. Okay, this whole operation is clear. Yes, if I draw the characteristics, so can you draw the characteristics? Yes, definitely we can draw the characteristics. Transfer characteristics. We generally call it transfer characteristics. Output characteristics, VDS and ID. So you see, when VGS equals to 0 volt. Okay, so what is happening whenever VDS equals to VGS equals to 0 volt, then what is happening? This current increases like that. Okay, when we increase the value of VDS, in that case, this drain to source current increases like that, and after certain time, this becomes saturated. So this is called saturation. Saturation region. Okay, and for VGS equals to 0, this current attains a maximum value, and this value is known as IDSS. IDSS. This is the maximum current, IDS. Okay, and one more thing. Suppose you are applying negative voltage here. Suppose you have started applying negative voltage. So what happens? VGS equals to minus 5 volt. Okay, minus 2 volt, minus 1 volt. Some negative value of the voltage has been applied. So what will happen? This channel will be closed earlier. You know that VDS will attain the value of BP earlier, and this maximum current will be reduce. And similarly for VGS equals to minus 2 volt, and finally VGS equals to minus 3 volt, and finally for this channel will be completely closed. Okay, so you see no current will be there, and this is called whenever VGS is very high, and VDS will attain the pinch off voltage. Okay, and this is called cutoff. No current will be flowing through. And you see here this region specifically. This region is called ohmic region. Ohmic region. Okay. In the characteristics of transistor, this region is called ohmic region. Okay. Always keep this in your brain. This is called ohmic region. Fine. And one more thing, we got to know that between drain to source terminal, the current remains maximum in the case whenever no voltage is applied on gate terminal. Fine. If you apply some positive voltage in that case or as well, this current will attain the similar level of this maximum value. Okay, and when we apply negative voltage between gate to source, this drain to source current reduces. Fine. So this is the transfer characteristics of JFET. Transfer characteristics. Okay, and at the input side, if I draw the characteristics, you see here I am applying VGS on the negative side. I am applying VGS on the negative side, and again this is IDS. Fine, this is IDS. So what will happen? So you see, for 0, VGS equals to 0 volt. IDS will be having some maximum value. Okay, and whenever we increase the value of VGS, this IDS reduces. Okay, you see. Do you understand this? That for VGS equals to 0 volt, IDS is having some maximum value. Okay, maximum value. Whenever you start applying the VGS in negative direction, this current reduces. Drain to source current reduces like that. So these are the transfer characteristics of for an channel JFET, N-type JFET or N-channel JFET. I hope these characteristics are clear to you. If you face any problem in these characteristics, please let me know. I'll explain. Yes, tell me.
Sir, if we apply VGS positive, then what is going to happen for IDS, sir?
If we apply positive VGS, then what will happen? Is that similar question you are asking?
What will happen to IDS?
Whatever this is what I was explaining now. If I apply positive VGS, then what will happen? Is this current will attain the saturation level. This current will attain this saturation level. This current cannot go beyond this maximum level. Okay?
Yes, sir.
So it is reducing. Okay? Okay. So, and there's question for you guys. Question is explain the operation and transfer characteristics for P type JFET. So this is the question for you. You have to find out the answer by yourself and you have to write the answer in your own words. Okay, the similar kind of operation you have to perform here and you can write in your own language. Fine. That is Shockley's equation.
टाइम हो गया सर
Okay, give me 1 second. This is the current equation. IDS ID equals to IDSS 1 minus DGS over VP whole square. This is called current equation. Okay. VP is pinch off voltage at which channel is completely closed. PGS, you know well, IDS is the maximum value of the current, and this is called Shockley's current equation. Tomorrow we'll try to verify these characteristics of JFET using this current equation. Fine, so we'll meet tomorrow.